Okay, we're all set up. Now let's quickly talk about this. Remember that we have our IGCSE chem. Let me put it for you here. Okay. I want to quickly show you. This is your IGCSE chem. 12 topics. And the topics that are interesting us right now, okay, the hard ones that we want to get out of the way and link up and do together was 6, which we did yesterday, okay, or 5 rather, which we did the day before yesterday, okay. 5, chemical energetics. We did it, and we did exothermic, endothermic, bond energy. You can check that video which I did for you guys. You just need to remember the formula for bond energy calculations. Then you have chapter 6, which is chemical reactions. Okay, chapter 6 is chemical reactions. This is the one which is split into the 3 sections we are doing today. One is going to be rate of reactions, so you just have to understand the rate of reactions and the factors that affect the rate of reactions, and you need to understand the collision theory because they'll ask you about it. Then you go to equilibrium, okay, the concept of equilibrium. Then from there you go to redox reactions. These are the 3 sections of chapter 6, and of course we have our chapter 11, organic chem, and chapter 12 that I want to talk about also. Okay, I was very much tempted, I almost did chapter 12 to prepare you for alternative to practical paper 6. We'll do it. Okay, quantitative analysis. We'll go through it together. Don't worry about it. Where you learn about the techniques of doing your experiments and all these other things. But as for today, we are doing the first part of chapter 6. It has 3 parts which we want to quickly go through it. First part is rate of reactions, then we do equilibria, and we do redox. We must know what we are expected to know in each of these sections without a problem. Are you ready? Are you ready, students? All right, so let's go for it. All right, so here, rate of reactions, that's what you must know at the end of the lesson. There'll be some few things that I'll say, but I won't waste your time. Right, anyway, the rate of reaction is how fast reactants get changed into products. How fast? It's about speed. When you say rate, you're saying the speed. How fast do you have your reactants converting to products? A faster rate means the reactants go to products much faster. Now, before you do this, you must first understand what a reaction is. Then you understand the rate of a reaction. So when you understand what a reaction is, you must know that a reaction is something that will bring a chemical change. This is background. Chemical change is different from physical. When we say we have a reaction, we are saying the substance has changed from within, from the inside. When a chemical reaction happens, then things change. This is different from here. This is a physical change. A physical change is not a reaction. We want to get this out of the way. When you see something melting or boiling or freezing or dissolving, or when you mix things together, that's not a reaction. That's not a reaction because no new substance is formed. If you take salt and you dissolve it into water, you just have salt dissolved in water. You don't form something new. But if you take salt and water, and if you ever were to react them and get something completely different, maybe even a gas or something completely different from water and salt, then that's a reaction. But this is not. When we have melting, these are physical changes. A physical change is not a reaction. So we want to get that out of the way. Okay, that is why we are doing this. We are getting it out of the way to say, students, a physical change is a change in something we can measure. A change in the state from melting. When we say it's melting, it's changing from solid to liquid. That's a physical change because it's a change we can observe and measure. Boiling is changing from liquid to gas. We can check it. We can see it. Freezing water is changing from liquid to solid. Dissolving is taking a solid, you make it disappear into a liquid. To dissolve is to disappear. That is not a reaction because there is no new substance formed. Always remember this. When you change state, it's not a new substance. When water, which was liquid, becomes ice blocks, this is not a new substance, it's the same substance. Only that their state has changed. Only that the state has changed. But when we have a reaction, a new substance is formed. So that's the only thing which we have talked about so far. The only thing which we have talked about so far is reaction is equal to chemical change, which is equal to new substance. Okay, chemical change, which is in bracket new substance. New substance. New substance. So a reaction is a chemical change, which is a new substance. So a new substance is formed. If no new substance gets formed, then we don't have a reaction. Forget about it. New substance formed. A completely new thing. Like you take hydrogen and oxygen, you get water. Huh? Can you imagine? Hydrogen was a gas. Oxygen was a gas. These are very, very different things from water. But you react, you get water. A completely new thing. That's a reaction. Okay? And it is difficult to reverse if you can reverse. It's very difficult. Okay? And remember that the chemical composition will change. In other words, we are saying the arrangement of atoms, it will change from atomic level. A new thing will be there. If you look inside this thing, it's completely different to what hydrogen was like and what oxygen was like. So there's chemical, there's change in the chemical composition. There is change in the atoms. New bonds form. This is a reaction. All right. Thank you for telling us that. Now, how do you see a chemical reaction? Yeah, things they are. Listen, we said a physical change is not a reaction. But I want you to know also that when a reaction happens, there can also be a physical change that happens. So basically, what we saw here was if no new substance gets formed, we do not have a reaction. If no new substance is formed, if the chemical composition remains the same, then we don't have a reaction. We have a mixture which is reversible. Okay? It's just the physical properties that have changed. The state from liquid to solid, from solid to liquid, from liquid to gas, that is not a reaction. So nothing has changed. The atoms are still the same. Their state is the only one that has changed, or arrangement. But now, when you have a reaction, we say that we have a new substance form. Now, when a new substance forms, you can have signs. You can have things that you will use to know, oh, a reaction has just happened. When something is going to go through things like this: color change, temperature change, smell produced, light produced, fizzing, effervescence is like when you open your Fanta and you see gas coming out of the liquid. That is a sign of a reaction. So when we talk about things we can see is the color change, the temperature change we can measure. A light can be produced, smell can be produced, pH can change, there can be effervescence. These are signs that a reaction has happened. But that's not the reaction. Reaction has happened at the atomic level, but there can be signs. Color, because a new substance has been formed. Temperature, because in any reaction, energy is released or absorbed. Released to the surroundings or absorbed from the surroundings. We just saw that. Or you can have energy released as light instead of heat. Smell, that is a new substance forms and then a new smell comes out. So this can happen. Signs of a chemical reaction, just know them, okay? Just know them. We'll see when you talk about them, especially when you keep moving with your chemistry and you now start to talk about what we call, what is the word? Precipitation reactions. You see this, I'm just trying to say, you see these things as you keep going with your chem. So you should always know it. So this is a table which summarizes. We said for physical change, no new substance is formed. For a chemical change, a new substance is formed. Okay. For a physical change, let me. Okay, and we said physical changes are reversible, blah, 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 blah. You can just have this. Examples is just change of state. For physical change, it's just a change of state. For here, it's a new substance completely forming. For example, rusting. Rusting, a new substance forms, or burning. When things burn, a completely new substance forms. When you burn firewood, you get a completely new thing. Anyway, now we are going to what we want to look at, which is the rate and how to measure the rate. Rate of a reaction is the speed at which a reaction is happening. And when we say the speed at which a reaction is happening, we are just saying the speed at which reactants are turned into products. That tells you the rate of a reaction. Speed at which reactants are converted into products. That's the definition which I want you to have. Now, when you look at this, there are 5 factors that possibly can affect your rate of reaction. Here are the 5, okay? 5 factors that can affect the speed at which a reaction is happening. Factor number 1, concentration. Factor number 2, pressure, surface area, temperature, and put a star on catalyst. Right. This is a very, very important subject which we're about to get into. Rate of reaction. So you must master rate of reaction, and then when we come to equilibrium, we are going to have things that affect equilibrium. I don't want you as students to confuse equilibrium and rate of reaction. That's completely different. When we start talking about equilibrium, we are going to be talking about a position where a reaction can get to. It has nothing to do with how fast a reaction is. That's a completely, so we'll be done with this. Don't mix up things. And I'll show you when you're doing questions, don't mix up things. So the 5 factors that can affect your rate, what are they? Concentration, which means the amount of something. You can change the amount of a liquid or solid in a solution. And when you don't have a solution, when you have gases, you talk about pressure. Then you're going to have surface area, you're going to have temperature, you're going to have catalyst. All these have the same effect. Look at this. When you increase the concentration, the rate will increase. Okay, the concentration of your reactants. When you increase the pressure of the gaseous reactants, the rate will increase. When you increase the surface area, the rate will increase. When you increase the temperature, the rate will increase. When you add a catalyst, the rate will increase. That's just basic. But before you say that, there's something which you're going to be asked about, which is the collision theory. Collision theory helps you to then explain what is going on. Collision theory is this. When we say you have a reaction, the only way you're going to have a reaction between 2 substances, A and B, is if they collide. So the only way that I'm going to have a reaction is the reactants must collide. So listen, this is a rule. It's called the collision theory. It says when you want a reaction to happen between any of your particles or whatever, they must collide. So there is no Bluetooth reaction. A reaction will only happen when 2 things come in contact. So the particles must collide. That's number 1. There are 3 things that collision theory says. So for a reaction to occur, it tells you conditions for a reaction to occur, period. It says for a reaction to occur, particles must collide. And number 2, they must collide with enough energy. If they collide like this, no reaction will happen. But if they come, they can react because they have enough energy to ignite each other for a reaction to happen. And number 3, particles must collide with the correct orientation. In other words, they must fit into each other. If they come in the wrong orientation, then they won't fit into each other and there will be no reaction. So particles must collide. They must collide with enough energy and in the correct orientation, which means they must be facing each other nicely. These are 3 things that the collision theory says. You cannot forget them. Okay, these are so easy. You can remember them all all the way till you're done. That collision theory, once you talk about collision theory, it is telling you what should happen for a reaction to occur. Particles must collide. That's why it's called collision theory. And they must collide with enough energy, and they must collide within the correct orientation. So it's all about collisions. They must collide. They must collide. And they must collide with enough energy for a reaction to happen. In other words, they must collide with energy that is greater than or equal to activation energy. If we say they must collide with enough energy, that means the energy should be at least the same as activation energy. That is what we mean by enough energy. So the particles must collide with enough energy and in the correct orientation. This is what makes a successful collision. The particles collide and they have enough energy and they rearrange to form products. Obviously, they'll be in the correct orientation. That's a successful collision. An unsuccessful collision can happen if particles collide but don't have enough energy or wrong orientation. If this happens, then no reaction will happen. This is a collision, but it's unsuccessful. Why is it unsuccessful? Yes, the particles have collided, so one of the conditions has been met, but maybe they don't have enough energy, or maybe they have enough energy, but they're in the wrong orientation. Then no reaction will happen. This takes us to this word, activation energy. This is just the amount of energy that is needed for a successful collision. The minimum amount of energy that you need for a successful collision. Okay, if you come and you collide and your energy is less than activation energy, then no reaction will happen. When you collide, the energy must be equal to or greater than activation energy. Okay, if particles have less energy than activation energy, no reaction. If particles have more energy than activation, reaction will occur. So activation energy is just the minimum amount of energy you need for a reaction to occur. Okay? Now, here, we are now looking at the 5 factors that we talked about. The 5 factors that affect your rate of reaction, right? Temperature, catalyst, concentration, surface area, pressure. Explaining each factor using the collision theory. How does concentration affect the rate? When you increase concentration, why do you have a faster reaction? Why? Because when you increase concentration, that means you're going to have more collisions and you're going to have more successful collisions and the rate increases. When you increase concentration, you will have more reactions. So concentration changes the number of collisions. When you increase the concentration, you will have more particles inside your solution, which means that there will be more collisions and more successful collisions. If you have more collisions, then there is a higher chance of having more successful collisions. If I only have 3 collisions, then my chance of having successful collisions is low. When I have 500 collisions, then in those 500 I can find 10 successful ones. So that's the good thing. More collisions will lead to more successful collisions, will lead to a higher rate. So that is what happens. Now, pressure, same story, similar story. Okay, more collisions. When you increase the pressure, particles are closer to each other. You get more collisions every second and more successful collisions. Why? Because you have more collisions. When you have more collisions, you will have more successful collisions. And this will be, the rate will increase. But this is only for gases. Please, higher pressure, faster reaction. Right, now let's go on. Surface area. We now need to talk about surface area. What happens with surface area? The greater the surface area, the faster the reaction. All of them, we know that. Why? Because smaller pieces expose more particles. Okay? Smaller pieces, when you are going to have a greater surface, This is one of the biggest problems I can have with people. When somebody hears that you have bigger surface area, they think you have a bigger substance. No! No, no, no. Increasing the surface area is not increasing the size. It's wrong. When you increase the size, you are actually reducing the surface area. So surface area is how much of this guy is exposed. How much of the area is exposed. So when you want to do this, you are going to take a big rock and grind it into many small particles. Now, if you add the surface area of all the small particles which you have, it will come out being larger than the surface area of the one container. So we are not saying one tiny rock has more surface area than, one tiny stone has more surface area than a rock. Of course, that's not what we are saying. But we are saying if you take a big rock and you crush it into many small particles, you are going to have a large surface area. Which large surface area? The combined one. The combined one. When you add the total here is more than the rock. So small particles have a larger exposed area. A larger exposed area will lead to more collisions, which will be more successful collisions, and the rate will increase. So this is important. Exposure. When smaller pieces expose more particles, and there will be more collisions, and thus you have more successful collisions and a higher rate. The rate will increase. Thank you, collision theory. Last one now. Is it the last one? No, the second from last. Temperature, then catalyst. Temperature is now related. We're going to summarize this. You must know all these 5. It's so important. It's so important. This is where the money is. Do you get me? When we say this is where the money is, we are saying this is the important part. Don't waste your energy knowing, oh, what does the definition of rate of reaction mean? Okay, you can meet that and that may give you 1 mark in the exam. But these ones, factors that affect rate, the collision theory, this is where the money is at. You are not allowed not to know it. You must know this. Make sure you know this. How does each of these factors affect rate? Don't run away. Face it and know it. For temperature, we say when you increase temperature, particles gain kinetic energy. This is so important. This is going to be, you're going to meet this a lot. Okay? When you increase temperature, particles gain more kinetic energy and they move faster. They move faster, which is leading us to this. When they move faster, you will have more collisions, yes, but also the most important thing is more energetic collisions. Listen, temperature gives the particles kinetic energy. Now they have more energy, so they will be colliding with serious energy, which means you are going to have a lot of particles having energy that is bigger than activation energy. So of course a reaction will come. So more particles have energy greater than activation energy. This is the secret of temperature. It's the only one which does this. It doesn't focus on number of collisions. Of course, there will be more collisions and more successful collisions. But the main reason why you will have more successful collisions is that more particles have energy greater than activation energy. So many more successful reactions will occur, or collisions will occur, and this increases the rate. Please, this factor they are showing you that it increases both number of collisions and energy of collisions. Most of these things we were learning, they were just increasing the number of collisions. This one will increase the number of collisions and the energy of collisions. Temperature? Yes. Don't let me down, hey. You are not allowed to let me down. When particles gain, or when you increase temperature, the particles gain kinetic energy, move faster, and they collide more frequently and with greater energy. Now, since more particles now have energy greater than activation energy, there will be more successful reactions, and the number of successful reactions will increase. Because for you to have a successful collision, not reaction, but a collision, for you to have a successful collision, your energy must be greater than activation energy. And that will happen if we increase your temperature. You gain kinetic energy, which means the energy in the collision is greater than, okay, the activation energy. And there will be more successful reactions. Then last one is catalyst. How does a catalyst speed up a reaction? Does it increase the number of collisions? No. Okay, here they are. First thing is the definition. It is a substance that speeds up a reaction but remains chemically unchanged or is not used up. You use one of these two. Speed up a reaction, but it is not used up in the reaction, or it remains chemically unchanged. So it will speed up a reaction without getting used up. That's a catalyst. It will speed up a reaction, but it will not be part of that reaction. It will just help it and go away. And how does it do it? Here's how it does it. It lowers the activation energy. Catalyst, remember, activation energy is the energy needed for a reaction to happen. Catalyst will say, this is the energy, activation energy. Let's say this is the activation energy. Look where it was here. Now it's been lowered. So a catalyst will lower the activation energy, which means that more collisions are now successful collisions. Why are we having more collisions now being successful collisions? Because more collisions now have energy greater than activation energy. Because the activation energy is now low. So more guys now have enough. Catalysts do not touch the particles. Don't talk about particles and catalyst in the same sentence. Catalyst will lower the activation energy, or it will provide a new path which has lower activation energy. So here, when activation energy is lower, more particles have enough energy to react. More successful collisions occur. Rate increases. Don't let me down. A successful collision, we talked about it, a successful collision. And we said a successful collision comes from particles reacting with enough energy in the correct orientation. Right. Here, you can have this as the last thing that you must know, and I'll give you questions. I'm happy if you know this. It's okay. How many factors do you have that affect rate? You must know collision. This looks easy, but this is where questions are coming from. For this chapter, this section we've just done is the bones. Bones. Not just anyone can bite it. It needs strong people, great people. Concentration. How do you affect the rate of reaction? When the concentration is increased, there will be more particles, which results in more collisions and more successful collisions, and the rate will increase. pressure, gas particles are brought closer together, which will lead to more collisions and which will result in more successful collisions, and gas particles have. There you have the surface area. No, let's talk pressure. Concentration, pressure, we talked about it. Area. Area now, you said it's about exposure. When you increase the surface area, you are not increasing the size. If somebody tells you that, you should say, hey man, hey. Increasing the surface area comes from decreasing the size. You grind something into small particles. You decrease the size. You are exposing more parts. So more particles get exposed, and there will be more collisions and more successful collisions. These three are out of the way. Now you go to catalyst and temperature. This is more collisions plus more energetic collisions. So here, when you increase the temperature, particles gain kinetic energy and they begin to move faster and collide more frequently and with greater energy. Oh, once you say such things, you are getting your marks now. You're getting your marks. Okay, we collide with greater energy, which means more successful collisions. As more collisions, we will now have energy greater than activation energy. Same for catalyst, but catalyst does it in a different way. It lowers the activation energy. And that means there will be more successful collisions. There will be more collisions with enough or with energy greater than or equal to activation energy. Are we together here? Have you seen this? Students, have you seen this? This should not be confused with equilibrium. I'm going to show you equilibrium. There's a few reactions that you talk about, but it's not necessary. I'm going to show you equilibrium and questions they ask you. Then we're going to do a few questions and see how it goes. In equilibrium, we're going to talk about a lot of processes, the Haber process, the contact process, and we are going to see the factors that are going to be in there. We'll talk about it tomorrow or in the next chem lesson. We compared with this. It's a completely different idea. Here we have ended collision theory and talking about this. That's the important part. Are we together? Okay. So don't let me down. Let me send you a few questions and let's see how good you are now. Dismissed.